This is the assignment 9 solutions. Question 1. A friend is helping you move a large couch. You are pulling horizontally in the direction the couch is moving, and your friend is pulling vertically upwards. Who's doing more work, and how do you know? You are doing more work. This is because the work that you do is at an angle of 0 between the displacement and the force that you apply, and the work that, or the force that your friend applies is perpendicular to the displacement of the couch, so your friend does 0 work. Your friend is helping though. Your friend helps by lowering the force of friction. This is because the force of friction is equal to the normal force, and when your friend pulls upwards, it lowers the normal force required to keep the box balanced with the force of gravity, so the force of friction becomes lower. Number 2, determine if the following are examples of positive, negative, or no work. This first one is positive, pushing a door open. You push the door in the same direction that the door moves, so the displacement is in the same direction as the force. Positive work. B, while catching a ball thrown to you, a force must be applied to the ball to bring it to a stop. Same idea here. The force applied is in the opposite direction as the displacement of the ball as it comes to a stop, so that is negative work. You can also think of that as a negative change in kinetic energy. The kinetic energy goes from something big to 0. So work is also equal to the change in kinetic energy, so negative work there. C, normal force acting on a sled, sliding down a hill. This is 0 work. They are perpendicular, the displacement and the normal force. Lastly, the braking force applied to an elevator while it comes to a stop. This is negative. The force is in the opposite direction as the elevator is moving because it is coming to a stop. Or again, the same reasoning for B, the change in kinetic energy gives you negative work. For question 3, an elevator of mass 1,500 kilograms is raised up 20 meters at a constant velocity. So first, I'm going to find the force of gravity, which is mg, which is 1,500 times 9.8, which gives me 14,700 newtons. So that is my force of gravity. And now I need to find the work. That is force times displacement times the angle, the cosine of the angle between them. So that is 14,700 times 20 times the cosine of 180 degrees. So the work due to gravity is going to be equal to negative 294,000 joules. This is not down, it's not a vector, this is a scalar, so we just say that this is negative work. That negative work comes from the cosine of 180, which is equal to negative 1. It is 180 degrees because gravity is pointing downwards, and the elevator, we are told, is moving upwards. So the force is pointing in the opposite direction as the displacement. So this here is our final answer. This is the work done by the applied force. Now we are told that this is a constant velocity, so applied force must be equal to the force of gravity. In magnitude, the direction must be opposite. So we are also going to have 14,700 times 20 times the cosine of the angle between them. This time it is 0 degrees, however, though, because now they are both pointing in the same direction. So we get the same number here, but positive instead of negative. And total work done ends up being both of the two works we just found added together. And there's our answer, 0 joules, I should say. 4. While driving onto the highway, you speed up from 50 kilometers per hour to 110 kilometers per hour over a distance of 300 meters. The total mass of the vehicle and its contents is 2,000 kilograms. We are looking for the change in kinetic energy of you and your vehicle. So that is going to be the final minus the initial. Factor out 1/2 m. That's Vf squared minus Vi squared. That's 1/2 times 2,000. And converting from kilometers per hour to meters per second, I get about 30.56 squared minus 13.89 squared. And this gives us a change in kinetic energy of about 740,981.5 joules. B, how much work did the engine do during this acceleration? Well, work is equal to the change in kinetic energy. So the amount of work done is the same. So those were questions 3 and 4. Question 5. The oh my god particle was an extremely fast-moving proton with uncertain origins that was detected here on Earth. It had a mass of 1.67 times 10 to the negative 27 kilograms and energy of 51.3 joules. How fast would you need to throw a 0.14 kilogram baseball to match the energy of this single proton? So the kinetic energy here is going to be equal to 1/2 mv squared. And we're told that it must have an energy of 51.3. We're told that the baseball has a mass of 0.14. And we're looking for velocity here. So the velocity is equal to 51.3 times 2 divided by 0.14 square rooted. And that gives us about 27 meters per second. Now for the optional bonus questions. Number 1, when you calculate the speed using kinetic energy, what do you notice about the speed of the oh my god particle? Using the same formula basically as above, but with the different mass for the proton. I get this number here. It is larger than the speed of light, which is why it's unrealistic. Because nothing can go faster than the speed of light. Number 2, I give you the true speed, and I tell you the speed of light, and using those numbers and the total energy measured, calculate the mass of the particle. So just writing out my formula for mass here. This is just the kinetic energy formula, but rearranged. And so here I get my fraction. So 0.999. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 16, 17, 18, 19, 20, 21, 22, 23 times 299,792,458 all squared, which is equal to about 1.14 times 10 to the negative 15 kilograms. And number 3, compare this calculated mass of the proton to the real mass of the proton given above. So 1.14 times 10 to the negative 15 versus 1.67 times 10 to the negative 27. Both of these in kilograms. So you can see that the calculated mass is significantly larger. What is that, about like 1 trillion times larger? Something like that? I don't know. But anyway, much larger. Explain why the mass of the particle must change. So in equals mc squared, if we just look at c as a velocity instead of the speed of light, conceptually this is just a decent way to think about it. Not rigorously correct, but conceptually this is fine. So as you have a very fast moving particle, and it's very close to the speed of light, if you're adding more energy to the particle, you cannot increase the speed any farther, so the mass has to increase. So for a particle, or I guess object in general, for an object moving close to the speed of light c, adding energy will increase mass because speed cannot reach or exceed the speed of light c. Okay, so for number 6, a rock is thrown vertically upwards at 10 meters per second from the top of the cliff. How fast will the rock be traveling when it hits the ground at the bottom of the cliff, 45 meters below where it was thrown from? So initially we have some initial gravitational potential energy, mgh, plus 1/2 mv squared, because it is thrown vertically upwards. And at the bottom, it has some kinetic energy as well, but no more gravitational potential energy. So I'm going to go ahead and cancel the mass, because that is the same for everything. And then I'm left with gh plus 1/2 vi squared equals 1/2 vf squared. Rearranging for vf, I get the square root of 2gh plus vi squared. That is what I end up with, and plugging in numbers, and I get 31.3 meters per second. Seven, a snowboarder rides down from a short mountain slope. At the top of the slope, the snowboarder is 600 meters above sea level, and at the bottom of the run, they are 450 meters above sea level. The change in the snowboarder's gravitational potential energy from the top to the bottom is -1 times 10 to the 5 joules. So calculate the mass of the snowboarder. So I know that the change in gravitational potential energy is equal to the final minus the initial gravitational potential energies. I'm told that the final is just equal to -10 to the 5. And I know that both of these have mg. So really it's just hf minus hi in here after I factor out mg. I'm looking for m, so rearranging, I get m equals -10 to the 5 over g times hf minus hi. Plugging in all the numbers now. I get 450 minus 600, and mass equals 68 kilograms. Plugging that all in. So moving on to question 8 here. A box starts from rest at the top of a 4-meter high ramp. The ramp is 5 meter long along its slope. The bottom 2 meters of the ramp has a rough surface with a coefficient of kinetic friction of 0.2. Top 3 meters of the ramp is frictionless. Excuse me, what is the speed of the box at the bottom of the ramp? So this here's my ramp. It's at some angle. We don't know what it is. We do know the one side length is 5, the other one is 4. I'm going to call this side length x, and I'm going to solve for that using Pythagorean theorem. Now, alternatively, you could have noticed that this was a special triangle and just immediately written 3 on this side length. Totally fine. Now, if I'm looking at the cosine of the angle theta, that is going to be equal to the adjacent side, 3, over the hypotenuse, 5, which is 0.6. So I'm going to write that the cosine of theta equals 0.6. And I will leave that off to the side for now and come back to that later. So initially at the top of the ramp, it has some initial gravitational potential energy, and at the bottom it will have only kinetic energy. However, some of that initial gravitational potential energy will be lost to work. So some of it will be lost. All right, so here we have some substitutions to do. mgh equals 1/2 mvf squared minus, now this is mu times the normal force times the displacement times the cosine of phi. Now phi is not theta, this is a different angle here. Phi is the angle between the displacement and the force of friction here. So substituting in some more, I get mgh equals 1/2 mvf squared minus coefficient of friction. Now, the normal force, this is going to be equal to the vertical component of gravity. So that's going to be mg cosine of theta, not of phi, multiplied by d, then the cosine of phi. So now I'm going to be able to cancel out the mass and write this as gh equals 1/2 vf squared minus mu g. Now, cosine of theta here, this is where the 0.6 comes from. I'll rewrite this so it's matching in color. That is where that 0.6 comes from. D, and then the cosine phi, friction has to be pointing up the ramp because the box is moving down the ramp. So this ends up being the cosine of 180 degrees in there, and rearrange, plugging in numbers, rearranging for VF, you'll end up getting 2GH, I guess I'll call this HI, because it's the initial height, plus 2 mu G times the 0.6 times 2, because that is the distance that friction acts along for, the bottom 2 meters, and then the cosine of 180. Plugging everything in, I get 8.58 meters per second. So somewhat a short solution, but more complicated. There are many different ways to do this problem. You could have broken this up into two smaller triangles as well and solved it that way by like actually finding what the angle theta is equal to and doing it that way. Could have absolutely done that, but I think this was the shortest method. So moving on to question 9. The bungee jumper. A 65-kilogram bungee jumper steps off a bridge that is 50 meters above the river below. The bungee cord is 25 meters long and acts like an ideal spring with a spring constant of 102 newtons per meter once it begins to stretch. Assume air resistance is negligible. Part A, determine the jumper's speed while they have fallen, or when they have fallen 30 meters below the bridge. The cord has stretched 5 meters at this point. So initially, they have some gravitational potential energy, and when they have fallen 30 meters, that is not the full distance, so they will still have some gravitational potential energy. The elastic bungee cord has not has begun stretching, so there will be some elastic potential, and they are falling, so we will have some kinetic energy in there as well. So doing some of our substitutions, mghi equals mghf plus 1/2 kx squared plus 1/2 mv squared. Plugging in numbers, we get 65 times 9.8 times 50 is equal to 65 times 9.8 times 20. If they have fallen 30 meters of the total 50, that means we have 20 left. That's where that came from. Plus the 1/2 times 102 times the stretch of 5 squared. So it's 25 meter long bungee cord, and they have fallen 30 meters, so 5 meter stretch there. And then plus 1/2 times 65 times v squared. We are looking for v, and plugging all that in and rearranging, you should get about 23.4 meters per second at that point. Part B, determine the maximum distance the jumper falls before momentarily coming to rest for the first time. So we are going to have our gravitational potential energy in the beginning. And because we don't know how far they fall, they have some final gravitational potential energy as well. We don't know what that is. It could be 0, it could be non-zero. We don't know what it is, so we got to include it. Plus the stretch of the spring. We know that this will be the maximum stretch as well. And because they momentarily come to rest, they will not have kinetic energy. Also, I meant to write this as elastic potential energy in here. There will not be kinetic energy. I jumped ahead with my substitution. Now I'm going to substitute mghi equals mghf plus 1/2 kx squared. Sorry. Now that's better. So if this here is my bridge, and this here is the river below, I know that this total distance is 50 meters. So I'm going to say that the total distance the person falls is y, and this is the distance from the bridge that they fall. So this little distance down here, the distance above the water they will be when they come to a stop, has to be 50 minus y. Has to be. And using very similar logic here, I know that the bungee cord is 25 meters long. So I know that the length of the stretch is this leftover 25 meters, is what I have left here, and I know that this is 25 meters. So I know that the length of the stretch can be modeled as y minus 25. So length of stretch is equal to y minus 25. And I'm going to go ahead and plug that in to my equations over here. So I get mg hi, which is just the 50 meters. And this is mg 50 minus y plus 1/2 k. And then for x, I have y minus 25 squared. Plugging everything in, number-wise, is going to give us 65 times 9.8 times 50 equals 65 times 9.8 times 50 minus y plus 1/2, 102 y minus 25 squared. Plugging that all in to a calculator gets you about 50 meters. So therefore, they stop at the surface of the water. So they just get dunked in, barely. And that was assignment 9. If you have any questions, please email me or ask me in class.